In this video, we're going to explore redox reactions that are very important for metabolism. So first, we're just going to start by talking about the most common electron carriers in the body, and those are nicotinamide adenine dinucleotide, or NAD, and flavin adenine dinucleotide, FAD. So NAD is right here, and here's FAD. Both NAD and FAD can go through reversible reduction oxidation reactions. So if we look at NAD here, the reduction is happening at the nicotinamide, where you have an hydride, which is a negatively charged hydrogen, more or less attaching to the nicotinamide, and that is how NADH can carry around electrons. And a similar thing happens with FADH as well, but we'll get to that in a second. So in the electron transport chain, the last molecule to receive electrons is oxygen, O2. Now O2 can only accept one electron at a time, which is a problem for NAD because it can only give off 2 electrons at a time. And so to accommodate that, one electron is given to oxygen, and the other electron is given to FAD. So FAD can have 2 different forms. One, it can be in its radical form or semi-quinone form, where it gets 1 hydrogen, and that hydrogen has 1 electron with it, and you form a radical. Or it can be in the complete reduced form or hydroquinone form, where it gets 2 hydrogens and it's no longer a free radical. So when given electrons to oxygen, FADH or FAD will be present to take the other electron away, because oxygen can only accept 1 at a time. Now let's talk about redox reactions in general. In redox reactions, you can think of them as group transfer reactions. That is, you're just transferring electrons from one group to another. And so we have an electron donor and an electron acceptor. The donor is the reducing agent, and the acceptor is the oxidizing agent. So remember the acronym oil rig. Oxidation is loss of electrons, reduction is gain of electrons. So if you're a donor, you have been oxidized and you cause something else to be reduced. That's why it's the reducing agent. So we can look at an example reaction where iron 3 plus copper goes to iron 2 plus and copper 2 plus. Now for redox reactions, and this D is supposed to be a double arrow, in these redox reactions, what you usually do to understand them is that you split them into half reactions. You have the reduction reaction where iron is gaining an electron to become iron 2 plus, an oxidation reaction where copper is losing an electron to become copper 2 plus. Remember, an electron is negatively charged, so if you gain one, you become more negative charge. If you lose one, you become more positive charge. Now, by separating redox reactions, you can create an electrochemical cell or a battery. So here we have a mixture of iron and a mixture of copper. By connecting these two through a linkage, electrons will naturally flow from the copper to the iron, and you can put a device in between this linkage, and that's how you get electricity from a battery. Now, to calculate how much energy you are getting out of a redox reaction, we need to use the Nernst equation. So we're going to look at some general reaction. A plus B goes to A plus B. And this is an oxidation reduction reaction. So on the left side, A is oxidized, B is reduced. On the right side, A is now reduced, B is oxidized. And the Nernst equation is this delta E. This E is a reduction potential. That is, how bad do you want an electron? Or how likely are you to undergo reduction? So the change in the change in reduction potential, we call that electromotive force, or EMF, or the electron pressure, or basically how many electrons are flowing. How much do the electrons want to flow? The bigger the EMF, the bigger they want to flow. Well, this is equal to the EMF under standard conditions, that's what this not means, minus RT, gas constant temperature, divided by N. N is the number of moles of electrons that are flowing through this reaction. F is a Faraday constant, multiplied by the natural log of the concentrations of products divided by the concentration of reactants. And once we solve for EMF, we can solve for delta G through this equation. Delta G equals minus NF delta E. So if you look at this equation, you'll notice if you get a positive electromotive force, you get a negative delta G, or that reaction is spontaneous. While if you get a negative delta E, that is not spontaneous. So if you know delta E, you know the reaction will be spontaneous based on its connection to delta G. So if we go back to our scheme of redox reactions, a lot of the times when people write redox reactions, they just write the reduction forms. And again, sorry, these D's are supposed to be double arrows, where A plus some number of electrons becomes A reduced, and B oxidized plus number of electrons becomes B reduced. If we use these equations, and we use the equation we used on the last slide, we can calculate reduction potentials for A and B as given here. Therefore, we can calculate the difference in reduction potential given by this. So when we calculate delta E, it's always going to be the reduction potential of the acceptor minus the donor. So what is accepting electrons? What is losing electrons? So what is reduced minus what is oxidized? And in biochemistry and inside the cell, we have a ton of compounds that go through redox reactions, so we have a ton of reduction potentials. And generally for reduction potentials, the higher the value, the better the electron acceptor, the more it wants to be reduced. While the more negative the value, the better the donor, more it wants to give off electrons. And a spontaneous transfer will happen if you pick one substance of the table. So for example, I'm picking NAD+. If I couple NAD+ with anything above it, I'm going to have a natural flow of electrons. However, this might not happen without an enzyme. Again, just because something's spontaneous doesn't mean it'll happen anytime soon. So proteins, enzymes, will help transfer these electrons. And if you notice, we have a lot of irons that are found in chromosomes, and these irons right here all have different potentials. What this is saying is that proteins actually modulate the reduction potentials of the metals they are bound to. So that is how the body can have different reduction potentials. And as we dive into metabolism more fully, you're going to see reduction potentials over and over and over again. So make sure we have the basics down now. That's it for this video. I will see you in the next one.